In this lecture, let's look at 3 examples on domain and range of a function. Let's start with a simple one. We want to evaluate the function notation. Given that the function f of x is x times square root of 3 minus x, let's evaluate f of 2, f of a, f of x plus 1, and f of x. The first one, f of 2. So we substitute 2 into the function. So we replace all the x in the function by 2. So this equals 2 times square root of 3 minus 2. 3 minus 2 is 1, so we have 2 times square root of 1, which equals to 2. The next one we have f of a. Similarly, but instead of a value, now we replace x by a, another variable. This equals a times square root of 3 minus a. How about f of x plus 1? So we replace all the x in the function by x plus 1, and we get x plus 1 times square root of 3 minus x plus 1. Let's simplify the square root. This equals x plus 1 times square root of 2 minus x. And the last one, f of x. So we substitute f of x into the function. The f of x is now the input. The function f of x is the input times square root of 3 minus the input. And the input now is f of x. So inside the bracket, I'll have another f of x. So here I have x times square root of 3 minus x. In the second bracket, I have another f of x. X times square root of 3 minus x. So that is f of x. Let's rewrite as x times square root of 3 minus x times square root of 3 minus x times square root of 3 minus x. In the second example, we want to determine whether or not each of the following relationships is a function. For each relationship that is a function, we'll also describe its natural domain and range, and determine whether or not it is a one-to-one function. And for each relationship that is not a function, describe the parts of the definition of a function that are violated. A. The rule G, from real number to real number, that assigns each real number x to the numbers whose square is x. That means if we have an input x, the machine or the rule will make the element to be the square root of the input. But not all the real numbers can be inside a square root. What's inside the square root has to be positive. So this rule is not a function, since the rule G maps from all real numbers to all real numbers. So the first part that violates the definition of a function is that negative real numbers do not have a real square root. For example, square root of negative 1 does not exist. But for each positive real number, they still have two numbers whose square is x. For example, square root of x and negative of square root of x. Their squares are both x. So this violates the definition of function again. We cannot map an input to two different outputs. For example, I can have square root of 2. This square equals to 2. But I can also have negative of square root of 2. This square also equals to 2. So rule G cannot be a function. How about part B? The relationship defined by this table. the first row we have the input, and the second row we have p of x, which is the output. Let's examine the inputs first. We have 1 to 6 with no repetition, so this relationship could be a function. Each input is mapped to exactly one output. Then the second question is whether this function is a one-to-one function. We can see that p of 3 equals to p of 6. The outputs for x equals to 3 and 6 both equal to 9. So this is a function, but this is not a one-to-one function. And the domain of the function, domain of p, includes values 1, 2, 3, 4, 5, and 6. So we use set notation. 1, 2, 3, 4, 5, and 6. And the range of the function, range of p, it includes numbers -1, 0, 2, 5, and 9. And this is not a one-to-one because p of 3 equals to p of 6. And part C, let P be the set of all living people in the world, and let W be the set of all women that have ever lived. Define F that map from P to W, so that each person is assigned to his or her biological mother. This is a function because each living person has only one biological mother, so it satisfies the definition of a function. However, this function is not one-to-one, because a mom could have more than one child, so we could map from two children to the same biological mother. How about part D? F of x equals 2 minus square root of x plus 1. This f of x is a function, because for each input that we put into the function, it will only give us exactly one output. Let's find its domain and range. Let's start with domain. What would be the possible set of values that we can put into the function? Note that the function we have a square root, and remember that inside the square root, we can only have positive numbers. So there's a constraint on the x. We need x plus 5 to be greater than or equals to 0, which means x has to be greater than or equals to -5. So the domain of f is from -5 inclusive to positive infinity. How about the range? We know that the result of a square root is always positive. So square root of x plus 5 is always greater than or equals to 0. So with the negative sign in front, negative of square root of x plus 5 will be always smaller than or equals to 0. Then if we add 2 on both sides, we get 2 minus square root of x plus 5 has to be smaller than or equals to 2. So that is the constraint on the y values. So the range of the function is from -infinity to 2 inclusive. Then the next question, is this function a one-to-one function? We can check that by substituting two different x values. Let f of a equals to f of b. So I chose a and b as my x values, and I suppose their y values are equal. And let's see if we can have different x values. So if f of a equals to f of b, then f of a is 2 minus square root of a plus 5. And that equals to f of b. F of b is 2 minus square root of b plus 5. I can cancel out the 2 on both sides, and I take the square on both sides. So I'm left with a plus 5 equals to b plus 5. Then I cancel out the 5, and I'm left with a equals to b. Which means in order for y values to be equal, the only way is to have the same x values. So this function is a one-to-one function. How about the last part, h of x? h of x equals to 1 over x squared plus 4. This is also a function because for each x value that we put into h of x, we'll only get exactly one output. So this is a function. Now let's find its domain and range. This function contains a quotient, and remember that we can never have 0 in the denominator. So the constraint on x for this function is that the denominator does not equal to 0. The denominator is x squared minus 4, and this cannot be 0, which means x squared cannot be 4, which also means x cannot be plus or minus 2. So the domain of the function, if we write it in interval notation, domain of h, that would be from negative infinity to negative 2, exclusive, because x cannot be negative 2. Then union. Union also means or, from negative 2 to 2, also exclusive. Then union, from 2 to positive infinity. How about the range? To find the range, I'm going to isolate for x from this function. So if I let y be the output of the function, so y equals 1 over x squared minus 4. And I isolate for x. So I multiply by x squared minus 4 on both sides. Then I divide it by y on both sides. So I get x squared minus 4 equals 1 over y. Then I plus 4 on both sides. So x squared equals 1 over y plus 4. Then I take the square root. So x equals plus or minus square root of 1 over y plus 4. Then what's the constraint on y in this equation? We have y in the denominator, which means y cannot be 0, because we cannot have a 0 in the denominator. And we have a square root, and we need the things inside the square root to be positive. So we also need 1 over y plus 4 is greater than or equals to 0. From here, I can rewrite it as 1 over y is greater than or equals to negative 4, which also means y has to be smaller than or equals to negative 1 over 4. And if y is a positive value, 1 over y will also be positive, which is greater than negative 4. So either y is smaller than negative of 1 over 4, or y is greater than or equals to 0. Then we have to combine both. Y cannot be 0 is the first condition. And the second part, we get y has to be smaller than or equals to negative 1 over 4, or greater than or equals to 0. So if we combine these two, we get range of the function, range of h, using the interval notation, from negative infinity to negative 1 over 4, union, from 0 to positive infinity. Then the next question, is this function a one-to-one function? Note we have the square in the function, so this cannot be a one-to-one function. For example, if I put 1, I will get the same value as if I put negative 1 into the function. And using a general notation, h of x is not one-to-one, since h of a equals h of negative a. So whatever the value I put into the function, I will get the same y value if I add a negative sign in front. Now let's look at the third example. Let's find the domain of the function f of x equals to square root of 1 minus 2x divided by x plus 1. Note that in this function we have a square root, we also have a quotient. So there are several constraints on the x. First of all, the denominator can never be 0. So the first constraint, denominator cannot be 0, which means x plus 1 does not equal to 0. That means x cannot be negative 1. And the second constraint, we have a square root, and what's inside the square root has to be positive. Inside the square root, we have a quotient. So what would be possible ways to get the positive values inside the square root? It's positive if and only if the numerator and the denominator have the same sign. Let's suppose both of them are positive. So 1 minus 2x is greater than or equals to 0, and x plus 1 is greater than or equals to 0. Then from the first inequality, I get 2x has to be smaller than or equals to 1, which means x has to be smaller than or equals to 1 over 2. And for the second inequality, I get x has to be greater than or equals to negative 1. How about if both of them are negative? So I can also have when 1 minus 2x is smaller than or equals to 0, and x plus 1 is smaller than or equals to 0. From the first inequality, I get 2x has to be greater than or equals to 1, which means x has to be greater than or equals to 1 over 2. And from the second inequality, I get x has to be smaller than or equals to 0. Then from the first option, when both of them are positive, then these two conditions have to met at the same time. I need x is smaller than or equals to half, and x has to be greater than or equals to negative 1. So from here, I get that x has to be between negative 1 and half. How about when both the numerator and denominator are negative? I get x has to be greater than or equals to half, and x has to be smaller than 0. I also need both conditions to met at the same time in order for the numerator and denominator have the same sign. But the intervals violate in this option here because I need a value that is greater than half but also smaller than 0. That is impossible. So this is not an option, none. Then the next step is to combine both conditions. The first one, which is denominator cannot be 0, we get that x cannot be negative 1. And the second one is we need what's inside the square root to be positive, and we get that x has to be between negative 1 and half. So if we combine these two, we get domain of the function has to be negative 1 exclusive to half inclusive. So using interval notation, domain of f is negative 1 using round bracket because it is exclusive until half inclusive. And that is the end of the lecture. In the next lecture, let's look at an example of function behavior.